It is my pleasure to introduce Sarah Margolis. Sarah Margolis began working with the Office of Science and Technology, NOAA Fisheries, this year as a Knauss Science Fellow. And she has been involved with many different technology initiatives. And this one is one of the projects that she was assigned. It's to look at how do we make the big data imagery accessible, not only to the NOAA enterprise, but to the wider community. And Sarah will give a demonstration on some of that framework and decisional type questions for the NOAA enterprise. With the decisional questions, of course, the important question is not only how we utilize it relative to the original objectives, but how do we utilize that relative to the new tools that are coming online. And Sarah will also give a demonstration of a 5-year initiative to develop an open source framework toolbox for doing automated image recognition for marine applications. So it is absolutely my pleasure to introduce Sarah.
Thank you so much, Bill. Hi, everyone in the NOAA Library, and hello to everyone tuning in at home or your office or tuning in with the webinar. Thank you so much for joining me on your lunch break post Labor Day. I hope everyone's had a wonderful holiday. So I'm a Knauss Fellow working in NOAA Fisheries Office of Science and Technology with the Advanced Sampling Technology Program. And today I wanted to talk to you about something that's becoming more relevant in the lives of scientists and with NOAA, and that's the idea of big data, because the more that technology increases, the more capability we have to collect information, and we're collecting large amounts of information. So we need to decide how to move forward with the big data, and specifically, I'm going to be talking about imagery data, images and video collected from the marine environment, and thinking about what do we need to do for the future, 5-10 years down the line, as new technologies and softwares, such as computer vision software, are becoming more readily available for us to use with our imagery and our data. So with my talk, I'm going to talk about 3 components of data management. First, we're going to think about imagery collections, the importance of collecting imagery and why we do it, and some considerations that we want to have in mind going down the line as far as making our imagery accessible. I also want to talk about storage, what you have to have in mind when dealing with large imagery data sets. You need to think about any archive requirements that your organization or agency might have. There are a lot of challenges with storage, so I'm going to talk about how to address them and moving forward. And also really starting to think about storage as far as accessibility goes and getting that accessible for the wider scientific community and the public. And as far as that accessibility goes, you need to think about any requirements if your data needs to be accessible, any benefits that you might receive from processing once the imagery is accessible, and using that accessible data for machine learning software such as computer vision software such as machine learning. So when talking about these 3 components of big data management, I'm going to weave in the example from our NOAA Fisheries perspective, talking about our imagery collections and where we're starting to think moving forward in the future. All right, so starting with those imagery collections, our importance. NOAA Fisheries creates a lot of data from imagery. We collect many things. One of our main missions is to do fish surveys across the United States. We also use optical technologies underwater to do habitat assessments and classification. We can use these optical technologies to collect real-time data. For example, if you put an ROV underwater, you can see in real time what's happening. And we use these optical technologies to really collect information on data-limited areas and areas that aren't sampled too much. Either they're not sampled at all, or they have limited data in them. So in recent years, we've seen an increase in optical technologies because the price is decreasing, they're becoming more readily available, and we're starting to use these technologies to do our fish surveys, habitat assessments. And we're also seeing in areas such as data limited areas, maybe in the Caribbean, that they also have an interest in starting to use these optical technologies to collect more information about their environment. So we're really starting to think, how can we use our imagery collections to get the most benefit from it in the future, looking forward down the line as we collect more and more. So I want to just talk a little bit about NOAA fisheries imagery that we have. So on the x-axis, sorry if I'm blocking anyone's way, on the x-axis we have our fisheries science centers. We have 6 fisheries science centers, and in the Pacific Islands we have the Southeast Fisheries Science Center, the Northeast Fisheries Science Center, Southwest, Northwest, and Alaska. And these blue bars represent currently in terabytes how much imagery we've already collected from our fisheries assessments and habitat information. So the lightest blue bar on the left is currently what we have, and projected in the future are the following bars. 5 to 10 years down the line, how much imagery can we expect coming into our centers? The Southeast collects a lot. We do a lot of information in the Gulf of Mexico and the Atlantic off of North Carolina and Florida. But the point is that imagery is going to keep on being collected as we try to resolve data limited situations and as we collect more information on expanding habitats and doing more fish surveys. So one of the first critical components when you're doing your data management is thinking about metadata. So metadata is information about the data that you have. So there are many different types, and the point is that your metadata has to be standardized and organized in a way that moving forward, your data is organized and readily available once you store it so that you can access it and pick out key components of your data and what you're looking for. So there are many different types. You have descriptive metadata that's talking about your type of data, any keywords, any learning objectives for the mission of your data. Technical metadata, talking about really descriptive information, if compression requirements or formats. Your subject metadata, which is really important, those are your annotations, and that's what's going to benefit the most from making your data accessible. So these are things that are actual textual representations of what is inside of your data. Then you have your structural metadata. Hierarchically, where does your data fall relative to one another? And that's just organization of it all. And your administrative data, metadata, that's talking about how long you need to keep it, your retention period, and access moving forward, requirements, and so on. So all these components of metadata, they will be particular to whatever data you're collecting, but the key is that it needs to be standardized and organized moving forward. So now let's talk a little bit about storage. So first is metadata. Now we're talking about, we've got all of our metadata organized for our imagery. Now we need to think about storage. So I want to talk a little bit about the status of NOAA fisheries optical data and how our data is stored. So as I mentioned, we have our 6 fisheries science centers, and each center collects information based on the missions of that science center and their projects that they have going on. So right now, and this is a very common situation for people that collect a lot of optical data, that the data is at the centers, they're collecting it and they're storing it in their own way. And if you want to access that data, you would need to find who knows about the data, how to contact them. They might even mail you the data on a hard drive. It's not super easily accessible. But there are some requirements for storage. For example, for NOAA, we have public access requirements, PAR. So it's required to be public to the access to the public and for the scientific community as well. We're also required to have archives. Our data must be archived for the long term, and I want to make the distinction that archives and storage are not quite the same, because archives are more for the requirements of your organization or your agency, and storage is going to have the data really easily accessible so you can process it quickly. You want to be mindful of any guidelines or standards that may exist when you're storing your data. So, for example, CMEX, the Coastal Classification, Marine and Ecological Classification System, you want to store your data with some type of standards that may exist to make the organization easy for accessibility. Future directions with storage for NOAA. When you're considering storage, so you really need to make accessibility key. That's the #1 thing that we're trying to do. We need to store the data, but it needs to be accessible when you process all this optical imagery. There are a lot of benefits from that, such as making it available for computer vision softwares and machine learning algorithms to help you process your data. So when you're storing your data, you need to consider that metadata that we talked about and make it very organized and standardized moving forward with it. You might want to have some timestamps on your data because you can easily reference your data to one another if there's a timestamp. Universal Coordinated Time, UTC, is one of the most popular choices for timestamping your data because it's time zone independent. You don't have to worry about what time zone you're in. And also coordinates are a really good idea to have on every set of imagery that you have, because then you can make them available through maybe like a user portal that's map-based, or people that want to look for your imagery via the location would be best. And when you're storing your data, you need to make sure that it is available for machine learning applications because they're readily available for us to use and to help process our data more efficiently. And here is just a figure of a AUV and an ROV that collects imagery. And I have a question mark: where are you going to store your data? Because there are some options that we have. So specifically for NOAA, NCEI, the National Centers of Environmental Information, hosts a lot of NOAA's data. For fisheries, it hosts all of our acoustics data, and they have the capability of hosting our optical data. They have the space for it. However, getting through the physical server and the firewalls and moving data all across the country to get to this centralized location takes time and is still in development. So right now, moving all of our optical imagery to NCEI would take a little bit of time as things are still in development. So right now, we can't put our data in NCEI. Something that is getting very popular are commercial options for cloud providers, such as Amazon or Google, names that you definitely would have heard of. They're incredibly popular, and they have the ability to have scalable platforms that can collect, that can host and disseminate the data quite readily. And accessibility is the key. So whenever you're thinking about storing your data, you need to think, how can I access this quickly for processing, for other people to access, and for things such as machine learning applications. So once you have your metadata organized, you have your data stored, how are users going to access your data? You need users to have access to your data so you can extend its purpose maybe beyond the original research mission. So you collect data for a reason, but you keep it so that other people can look back, discover new trends, new patterns, new ideas for later on. And that's the whole purpose of science and discovering. So you want to make sure that you have access by a user portal. And some really good examples are the OER video portal and NCOS biomapper portal. And I'll show you an example in a second. But whatever you do, you want to make sure that your subject metadata, your annotations, are in place and they're organized so that when users have access to the portal, they can easily find what they're looking for. So here's an example of the OER video portal. And as you can see, you can search from dates, you can search from depths and the map, and all this information that would be in the metadata. So you want to think about the curation of the data from the collection process all the way to the accessibility, what you need to have in your metadata so that it's accessible by something like a user portal that can have all that information in there, what users are going to be looking for. So once you have metadata, you have it stored and it's accessible to people, it's also accessible to machine learning. Who here has heard of machine learning? Almost everyone. It's in our everyday lives. On Facebook, you can see facial recognition. That's an example of machine learning. So machine learning is basically getting computers to act without explicitly programming them. You give them a little bit of training. Well, sometimes they need a lot of training, and with that training over time, they get better and they can understand what you're looking for because they can't think on their own like we do. So you provide them that training and the algorithms increase in their accuracy. So this is an example. This is a neural network on the side, and basically you have an input coming in and you have these algorithms that are trying to pick out features and determine weights and percentages of how important those features are, and they make a best guess of what the image is and annotate that. So if you have your information, let's see if the mouse is here. All right, so if you have your images and your video, your imagery, and you use this machine learning software, and the machine learning softwares can make classifiers, they can classify what's in the video, they can make detectors, they can just detect objects. And once they create those and they do an analysis, it can store the data and make it available in a graphical user interface, a GUI, that is an iterative process of storing and making accessible for you to access. With that machine learning software, you can use that for making your annotations and use other analysis features that it has. And then you can get an output of your data, which is either annotated data or more information of it. So it's really going to be critical in the processing that has to take place with our large amounts of imagery that we're collecting. So machine learning and how it can make your data even more accessible. So it'll automate annotations within your imagery, which is very cool. Here's a picture I have of, this is just a simple object detection. So let's say you feed in the imagery, goes through the algorithm, and it can pick out, I think that's an object of interest right there. It can do object detection, it can identify species, it can count fish, it can measure fish, and all of these things can create annotations that are a very laborious process for humans when they're processing their data. So this is going to be really important moving forward as we collect more data to be able to have a supplement such as machine learning to the human processing. So as I mentioned before, when you're using machine learning, training is exceptionally important. So NMFS, the past 5 years, we funded a project, an automated imaging analysis initiative, to create an end-to-end software that would be able to take imagery and annotate it and automatically process it. So what we created is called BIAME, Video and Image Analytics for the Marine Environment. And this software is an automated toolbox. It's online, and it uses machine learning algorithms to streamline that processing. So within the 5 years, we've had to train our dating sets and how to get our algorithms smarter. And so here I just have 2 examples of training data sets that we were using. There's supposed to be a double R in Bering Sea pollock. So in the Northwest, we have a pollock survey with cameras in the cod end of the trawl, and the pollock come in, and this BIAME software can count and measure the fish as they come through it in real time, which is very cool. This is an example of what I would say is an easier training set because the background is not very complicated. There's not a lot of species, and an image that like this would be easier for the algorithm to train with some training examples. And on the bottom here in the Northeast, we have scallop surveys going on with our HAB cam. It's a towed cam. It takes pictures that mosaic them together. This one is also continually training the algorithms. It's a little bit more difficult because as you can see, the scallops could be a similar color to the sand behind them. Some are white, some are brown, and the edges could be difficult to detect. But for the scallop survey, we just don't take pictures of scallops. Sometimes there are other things in the images as well. So in the Northeast, they've been using BIAME to detect skates that are in the pictures, and that's been going pretty well. They've been using that for the past year, although the BIAME training just rolled out in 2018, and we just finished training all the fisheries science centers, which is pretty cool. So why machine learning is so great? There are a lot of challenges when it comes to annotating imagery and processing imagery. Number one, the volume of it can be immense. So you can collect thousands of hours of video that someone has to go through. In some cases, they may not even be annotating or processing the whole thing. They may take a chunk, wait a minute, take another chunk and process it. And counts and estimates just become more accurate when you can actually process all of the data, and that's something that machines are going to have to start helping humans to do. For example, if you have a set of imagery that has really similar looking species, and in the underwater environment, it's difficult to see sometimes because there's turbid water, or it's not clear, or there's cloud cover. And so with machine learning, it can have detection of specific features that may be hard for humans to see on their own, but because the algorithms are working at such a small pixel level, they can pick out the features in an analysis a bit better than humans. Double counting from either individual fish swimming in and out of the frame that you're not sure if that's the same fish or not. Machine learning can create track annotations where it identifies that fish, and as it swims in and out of the frame, it knows it's that fish. So that can eliminate double counting. So machine learning has an incredible amount of benefits that definitely need to be used when we're thinking about processing our data. Okay. So last week, I actually went down to the Southeast Fisheries Science Center, and I sat in myself on one of these trainings. So what we were doing is BIAME and the company Kitware went around to all the fishery science centers, and the scientists that are actually going to be using the data and trying to process it all, sat down on their computers, got trained on their computers and how to start using BIAME and machine learning. So I sat down. I have never processed imagery before, so I'm going to give you guys a first look on some of the capabilities that BIAME and machine learning has. So if you guys would like to see a quick demo, try to pull that up for you. Okay, and I would also like to point out that this is a free software. It's online, and instructions and more information is available all online. And the instruction set is a living document. It's a PDF that's always changing. So as things are currently being updated, you can see how to move forward with that. Okay, so what I just did was I opened up a query GUI, and the GUI is the graphical user interface. So what I need to do is open that up. I'll create a new query type. And here I'm going to use imagery examples. So I'll load up my imagery. And I'm going to use an example from a mouse data set. And the mouse data set is just a stereo camera taken from the Pacific Islands that has some still images that on the bottom you can see it's loading. So it's pulling up the images. And right now it's thinking. It looks through an image and it says, I wonder what it wants me to detect, and it'll come up with a couple boxes. And from there, I have to tell it what I'm interested in, because although, you know, computers are very smart, they still can't read minds. So I'm going to let this load up for a little bit. And this is just one example. And I do want to reiterate that when you're training your machine learning algorithms, you have to be using training data sets that are similar to the ones that you're actually going to process, because that's what the algorithms are learning. They're learning what you want it to look for and what you don't want it to look for. So it says it's processing. Thank you for your patience. And it's actually quite cool. It has a lot of capabilities. And what I'll show you is just a model of a very quick, simple model. So here, do you see all these boxes that came up? They are guessing that I think this might be something, this might be something. So step number one is I actually have to show it what I'm looking for. So there's actually a triggerfish up in the top middle, and I'm going to click on this box, press this arrow. This is just how the program works. There's step-by-step instructions online. So I highlighted the box. I said this, everything, all these features in this box, this object is what I want you to look for. So I'm going to hit OK. I'm going to hit OK again. And it's going to open up. It's going to now look through the entire set of imagery that I wanted to look at. This is just a map view that it's not really important. And it's going to guess based on what I just told it, that fish and those features. It's going to go through and guess what I want to see. So up here are the score is how confident it is that what it's about to show me is what I guessed or what I told it to guess. So it came up, that's the triggerfish, that's one of my images, and here's how you start training it. So you either have to tell it, yes, that's what I want, no, that's not what I want, or ignore it completely. And when you tell it that's what I want, and when you tell it that's not what I want, you're training the algorithms. If you say to ignore it, then it doesn't learn from that at all, it'll ignore it. An example of that is maybe if you have two fish behind each other, and they're both the fish that you want, but within the box, you have those two fish, and you don't want it to learn the features of two fish in front of each other, because that is not a single fish. So in that case, they might have the features of the fish that I'm looking for, but because I don't want it to start identifying two fishes as one, I'll just say it's not relevant. So I'm just going to hit the plus key as I go through. So these are things that I'm looking for. I'll go a bit faster. As you can see, these are different. So here's, I'm telling it yes. Okay, so this one, because it has that other fish behind it, I'm not going to tell it no, but I'm going to right click and I'm going to hit rate as unrated. I don't want it to rate that one. So you'll go through, I'm just going to go through fast so you can see that there are other fish in here. Let's see. All right, so this one is definitely not what I'm looking for. So I'm going to start telling it, but these are not what I want. Okay, so in the top, sorry, that's what I want. you can see that that is what's going on. In the bottom, these are ones that it really wasn't sure. So it was on the boundary of, I'm not sure if it's this, I'm not sure if it's that. So this is the rating of how close it thinks it is on the top, and on the bottom, these are ones that were really on the fence for it. So I can say that's okay. I'm gonna say, do my unrating for this one, not rated. And then you'll basically just go through and do these iterations. And once you do, you train it. Maybe you want like a good handful of them. You'll hit refine. And what that does is that's literally you training the algorithm. It's saying, okay, based on now the information that you just told me and you clarified, I'm going to go through the set of imagery one more time, and I'm going to see if I can get a little closer to what I think you're talking about. And it'll pull up, so it puts the sets that I said that are correct up top, and then it starts to reorder them with maybe guesses that are a little closer, and it'll do that on the top and bottom. And I'm not going to take up too much time going through it again because I was just trying to do it fast. But if you were actually processing your data, you'd want to make sure that you were training it very correctly. So this is one that I would say is not relevant because it does have the 2 triggerfish in it, but because it has 2, I don't want it to start detecting those and counting it as 1. So that was, let me see if I can X out of this. So that is how you train. And so once you do the training, you would export that model. And then that model you can apply to other training data sets, which is very cool. So I'm going to hop back on to my PowerPoint because that was just what I wanted to show you for that. Okay, so that was a little bit of the demonstration. I have a couple minutes left, and I just wanted to say that machine learning has been used for decades, and now it's really readily available for computer processing, especially for underwater imagery, which is really difficult, and there's always a lot of it that's coming in. When you collect your data, you want to make sure that you're organizing your metadata, that it's standardized moving forward, and that you think about storage so that it can be made accessible, not just for the wider public, the scientific community, but for things just as I showed you, like the machine learning software. You want to be mindful if there's any guidelines or requirements or standards that exist or that you have to adhere to for either the NOAA mission or for your own agency and organization. And there are also some things that help your data, such as timestamps and being able to relate it back to one another. Those archive requirements may not be your storage, so you want to archive your data for the long run, but that's not going to be the quick storage that's going to make your data easily accessible. And you want to also keep in mind that when you use machine learning, you need to train the algorithms, and they can train pretty well, but you need to take the time to tell it what you want and what you don't want so that you can start applying them to your data. And with that, it's about 12:30, so I'll finish up. If anyone has any questions, thank you so much. You can take them now.
Do we have any questions in the room?
Yeah.
Do these machines have the ability to predict survival of given species?
The question was, do the algorithms have the ability to predict survival of the species? For this particular program, which is the only one that I'm familiar with, I know there might be others out there, it does not. It's only what you can actually train it, and you wouldn't be able to really train it unless the fish like had specific features that it looked like it was going to die. I'm not sure. Like, you know, maybe it was missing a fin. Maybe they could be trained to say, oh, this fish will have this % chance to live. Yeah, but that's just a guess.
You know, there's a further overlay I was thinking as you're presenting that using blockchain and artificial intelligence, you could bring in your governance, your guidance documents, and then associate them directly with your metadata, and then turn that into a search parameter. And that's the, you know, that's the big picture. Yeah. I'm sure you're thinking of that.
I definitely think that it has the capability to integrate things such as that, and it's still kind of in development, but that I think the possibilities are honestly endless. So
yeah. Exactly.
Cool. Anyone else? Yeah.
Hi, Sarah. Thanks for your presentation. So obviously this would have utility within a lab or an academic community where you're doing a similar survey across a region. But it seems the utility would really be broadened across at least a marine ecosystem or nationally if these probabilistic databases were integrated, right? So that you almost had a single database.
Right.
what's the community think about how to go about doing that?
There's definitely thought about doing that, especially within the fisheries science. I'm sorry, I didn't repeat the question. The thought was, what is moving forward about integrating the training data sets to one another. And right now, that's not in place, but people have definitely spoken about it because they know, for example, the Gulf of Mexico and Pacific Islands have pretty similar surveys. They do the reef surveys, which their algorithms that they train would benefit from one another. So that's the direction that we're starting to go because people recognize that it'll be beneficial to use the training that we've made to share with others. So it's a good point. Thank you. Okay.
So I think one of your graphs you showed maybe the Southeast Fisheries Science Center had like 500 terabytes of video or imagery or something like that. Is your sense is that these data are spread out on 500 hard drives, or do they have some sort of a common storage environment for their imagery data?
Good question. So the question was specifically for the Southeast Fisheries Science Center that has the most amount of our data, are the data collections stored in one spot or are they separate? And they're pretty separate. So in the Southeast we have several different centers in North Carolina, Mississippi, and Florida. And as far as I know, the imagery collections are each at the centers based on their own projects. There's no integration, which is something that we need to start to think about moving forward. We want to think about, should we start centralizing that storage, especially for similar regions such as the Southeast. So yeah.
There's another sort of program that is working to use fish image data, fishery dependent data, and seems to me there ought to be a way to integrate those two. I know it's not your job to do that, but it's not just fish surveys that need imagery.
So the comment was that there are other parts of NMFS that are collecting optical imagery, such as the electronic monitoring of fishery dependent data. And that is a different situation where there are considerations for confidentiality, because you'll be on an individual fishing boat that you don't want to make that data necessarily accessible to the public. And so they are also looking into the machine learning. So they would have to go about it in a way where they're very considerate of how accessible they're making their data, but as long as it's accessible for softwares that can help with their process, and they are making efforts on that.
It's still the same species though.
Yes, exactly. So perhaps the training algorithms can also be shared across. Yeah.
We have a few questions online.
Okay.
Is there any imagery or video file formats that are recommended for making this data available for machine learning?
There are. So whatever, if you're using BIAME specifically online on their website, which I can provide maybe like a link if we upload this presentation, but they're specifics, and so I would look online in the information. And as far as making your data accessible in other ways, there are recommendations that are online that I'm writing a report on this, and I'll actually have some of those recommendations written in the report that hopefully will be available soon.
Another question. Jordan's asking, as an archivist, can machine learning like BIAME or another program be used to identify people and places in archival images?
So do they hear the question when you ask it, or do I have to repeat it? Okay. Okay. So archived images, as long as, for what I know, archived imagery, it takes, because it's deep storage, it takes a little bit of time to get out. But if you can get the imagery out, you can use it with machine learning applications. BIAME in specific is for an underwater environment, so that's how the algorithms are trained. But there's definitely machine learning for people, and I think maybe like the Department of Defense would definitely have more information on that.
One more question. Do you know what programming language the main code is written in?
No, I do not.
Any more questions in the room?
Yes.
Has this been scaled to create or develop some products out there for fishermen?
Products?
Yeah.
I don't know about, so the question was, has this been scaled to create products? It's still continually in development as the algorithms are always being changed and updated. It's publicly available. I don't know if there, unless you can like, go online and follow the instructions, I don't know if there's like a set product package you can get, but it's, developments happen like rather quickly as far as like management time scales go. So I feel like that's definitely in the future that could be, but not right now. Okay.
So I don't think there's any more. So thank you, Sarah.
Okay, thank you. And I wanted to just thank everyone again for sharing their lunch hour with me. I know that, it's a special time of the day.